Okay, thank you. So I guess the title was Oracle Graph Strategy, but really the title I have is, graph databases, do we need to reinvent the wheel? So don't take anything I say as seriously. So first, everybody, I don't need to talk about this. Graph is a powerful tool, but sometimes we have to think about how to present graph to relational people. We're at Oracle, a database company, talking to them about graph processing. Well, we can do this with SQL. Why should we care? And so we have to explain to them, well, what is it good for? And so really, it's to me, graph technology is really about the ability to analyze data once it's represented as a graph. So basically, by representing your data as a graph, at least I'm coming at it from the analytic perspective, you capture fine-grained, arbitrary relationships between your data entities. So you basically could start out with some relational data, and then you kind of map into a graph, and that enables you to start analyzing this graph by leveraging the sometimes implicit information that would be hard to just kind of extract if you were just starting from tables and all you had to play with is the relational toolbox. And the most important thing here is that some of these complicated analysis can still be implemented using SQL, but the query will never finish or it will take a long time because you continuously are computing joins. So really, to me, graph processing is about recognizing that some relationships are special, and those relationships deserve to be materialized in terms of their joins because you're going to be traversing them quite a bit. So I'll give you an example. So you could start out with some product transactions, a bunch of purchase records. And then what you could do is take those purchase records and then map them into a graph, a bipartite graph, where you have customers as nodes, items that they've purchased as other nodes, and then links between the customers and the items they've purchased. And then you can formulate an algorithm, which is an iterative graph algorithm, where you essentially keep looking for each customer, consider which items they bought, and you can store that in some kind of vector defined per node. And then for each item, consider which customers have bought these items. And then you basically repeat this procedure until the information converges. And then you can start essentially looking at recommending higher score items. So you can look at the customers and recommend high scoring items that they haven't purchased as recommendations for things they should look at purchasing. And this is an example of collaborative filtering. So here I want to show two things. One is this kind of the advantage of using graph analysis. And two, showing that, typically people think of this as machine learning, but there's a dual here that people need to think about. But the question is, okay, so graph analysis is great for, graph is great for graph analysis, but how about data management? Data management is a hard problem. There's a lot of issues, dealing with concurrent transactions and all that entails. Lots and lots of other things, when you build an actual industrial strength data management solution. So is graph, particularly graph, is it adding anything to that equation? Is it adding anything? Is it making any of these things simpler? Does it require a new data management solution, or do we have already a fairly good solution for it? What we're missing is maybe the graph analytical engine to go along with the graph database, and the transactional bit. Maybe that's not something we need to invent again. Basically. And so what are we looking for? Are we looking for a new data management solution? We're looking for a solution that gives us fast graph analytics. So our approach has been to start out with something that we already have that's pretty good at the transactional bit, and essentially store the data. And we'll talk about later. Another reason why we're pursuing this is because a lot of existing data that people care about that could be mapped into a graph is already starting in a relational system. But let's say you even want to create new data. Well, why can't you, and you want to transact on it, well, why can't you store it just as a graph data model, either RDF or property graphs? We can map that into the Oracle database. And so RDF has already been traditionally an option for our databases, and now we're working on adding property graphs support in Oracle database. And then marry that system with an in-memory analytical engine, which has some support for fast bulk loading of graph data from the database, And so once you have that, you essentially can still satisfy transactional clients. Those would be served by the database. Analytical clients are served by the analytical engine. And the analytical engine could be listening to the database, essentially capturing the deltas and applying them either explicitly or implicitly, basically either on a timer basis or when the user wants to get a fresh graph.
Before you continue, down there at the bottom, it sounds like Oracle is managing RDF in relational structures.
That's correct.
Well, is it the case that the RDF support within Oracle is based on the spatial optional cartridge or whatever? And
yes.
Graph-based representation of the relational.
But stored in the relational database tables. So the only tweaks we do is that we change the optimizer to reason about this. Maybe they'll add more operators. Maybe they'll add special indices, right, to make things run faster. But the core structures at the end are still the relational structures. That way we don't have to worry about manageability, backup, all that stuff is handled by the database. So that's the approach. So the kind of model this implies, at least on the analytical side, so maybe I misspoke earlier. On the query side, obviously we support whatever the database supports. So it's, most people set it to read committed. So that's what we support on the transactional query side. But at least on the analytical side, the implication is basically a snapshot consistency model where, because we assume only a few concurrent analytic client at a moment are running, and each client runs for a long time. And these analytic clients tend to look at the whole graph, so they want a stable snapshot. All these algorithms are defined for essentially an unchanging graph. So this implies to us to provide some kind of snapshot consistency. So essentially, you take the database we can load as of time. So you can specify, you can tell the database, give me a version number, load the graph as of that time. A client can come in and start working on that snapshot. Another client can join and share that snapshot. So we're not creating one snapshot per client, but the client can also come in, one of the clients can decide, well, I'd like to have a fresher version of my graph. So now you apply a delta and get a new snapshot. And then when one of the clients essentially doesn't need a snapshot, then we can drop that snapshot as well. And in terms of scalability, because the database is the source of truth, it's trivially scalable. You basically just add more and more servers. The more and more clients you want to support, the more and more servers you have, and each client can be essentially loads its own snapshot. So the other thing that we're focusing on is we're not trying to come up with a solution that does both, that is out of core or supports out of core. We have an in-memory solution, at least for the analytics. For the query, obviously we support the database, or the database supports us. So why in memory? Obviously, graph does a lot of random data access. Graph analysis involves a lot of random data access, and traditional disk-based systems, obviously don't perform well for such workloads. And so this is performance from our in-memory single-node system, comparing. So this is time. Running triangle counting on, I think this is the web UK graph, so about 5.3 billion edges running on a single machine. This is PGX running on a single machine. This is PGX running on a Spark machine, which has more threads, and then comparing that to GraphLab running on 2 machines or 16 machines. So even at 16 machines, using a single machine of same machine using PGX is faster, and comparing that to the out-of-core disk-based solution that you'd get if you were to implement this in SQL. We also support, subgraph isomorphism. So we load up LUBM, transform it into property graphs, and then we can translate Sparkle into our own property graph query language. And so here we show at least 2 orders of magnitude at this point, probably can get to 3 orders of magnitude performance differential between the disk-based approach and an in-memory approach on graph pattern matching. So obviously we're recommending people to use very large machines, try to essentially, if you use, and we have pretty large machines, so Oracle can sell you today, if you have the money, 32 terabytes of DRAM, in a like single box, right? And you don't have to worry about distribution. So how many of you guys have data sets, or how many guys do you know have data sets that are bigger than 32 terabytes? I know there's a few, but 1%, 0.00. How many zeros after that, decimal do you need to get to? So the, huh?
How many zeros you have in the price?
It's not. It's certainly above 1 million, but it's not. It has to be competitive. It has to be competitive with clusters of the same size of RAM and things like that, right? So the premium isn't as high as you think. So that's the good part about these kinds of machines: simple programming, fast, kind of in memory. But the problem is, not everybody can afford one or want to buy one. Some people believe in like having a bunch more machines, right? And so we don't believe in building a cluster of wimpy machines. That's certainly not what we're going to target. But we think it's reasonable if people want to build a cluster of reasonably decent machines. So again, today you can buy an X4. Each rack will give you about 300 cores and about 15 terabytes of DRAM, right? So you can get pretty good density per rack. And so much more scalable, but the problem is now you have to deal with this communication latency as you're crossing nodes, and programmability is much harder, right? So, and so this is where on this side you have the things like giraffe and vertex centric, and people have to kind of start thinking, how am I going to implement my algorithm using these different programming models? Here you can write a for loop, throw OpenMP on it, and you're done, right? So how can we efficiently target these different approaches without sacrificing performance and productivity? Because the issue here is most people just build this, even though most customers don't need this, right? Because maybe someday I'm going to need to scale out. So they're essentially decreasing their performance, complicating programmability, just for maybe in the future we need to scale out, right? So our approach has been to use a domain-specific language to express the algorithms. This is a lot like SQL. Use SQL, and then you could, have a high performance single node implementation as well as distributed. So the users implement their program using a DSL. We have high level semantics, graph semantics. I'll show you an example. Intuitive syntax. If you understand graphs, you should be able to use our DSLs. That's at least some of the feedback we've gotten from people trying it out. And we provide compilers for the DSL, which understand the semantics of the language. They understand the notion of a graph, and they can apply domain-specific optimizations. A lot of cool domain-specific optimizations that are graph-oriented, like flipping edges, and basically instead of pulling information, we can push information, things like that. And then what we do is we build optimized execution engines. We don't try to build a system that fits all. We actually build specialized systems for each kind of deployment. So we have a really good system for scale up, and we have also building a system for distributed execution. So we optimize for each type of environment, and then we have the compiler essentially generating very different code for each of the systems. This is nothing groundbreaking for people in the SQL community, I guess. So just to give you a quick example of Green Marl. So this is very fuzzy pseudocode of between centrality. And the Green Marl equivalent is actually quite, a little bit shorter than pseudocode. And the reason is if you stare at the pseudocode, you'll notice that they actually are implementing breadth-first search as opposed to just saying do a breadth-first search. And so basically we start out by initializing between the centrality value for all nodes, and then we iterate for every node. We do a breadth-first search. Notice we have the breadth-first search construct. So it's an in BFS, and we're computing sigma. We're computing sigma of the vertex from the sigma of the neighbors, or of the up neighbors, the parents. And then we do a reverse breadth-first search where we're computing delta from the down neighbors, or my children, and then we accumulate into the BC value. So, this is actually pretty imperative, step by step, kind of like you pick up the algorithm, pseudocode. You can come in and kind of write it out. It's not that complicated. Now, go as a homework assignment. Try to implement this in a giraffe programming model or vertex-centric or whatever those new APIs. You'll find that it's actually quite challenging. So we believe actually we should just provide something like this, an imperative, imperative intuitive programming language. So I had some open discussion items for the group, but I think I already brought these up. So there are two different graph models. You guys are well aware of this: RDF versus property graphs. Right, and there's not a standard on property graphs, but Blueprint can be considered as a standard. So, do we actually need those things? Are the differences fundamental? I think this is what some of the OLAF is trying to tackle, or they're rather historical and marketing oriented. Are they going to converge? Do we see convergence here? Is property graph going to steal enough good ideas from RDF that basically people don't have to make another choice? Will one of them die out? Will property graph just be simple enough that people are just going to all use it, and then RDF will die out? Or is RDF already, used in enough critical system that will, be COBOL? It won't be like it won't die out, but it will not be the big thing. And so, what model should I use? Can we automatically transform from one model to the other, right? And the other question is, do we even actually need these graph models, especially, what we're encountering is a lot of people that already have existing data in relational stores. They're trying to do some graph analysis with that. So do we need to actually get them to transform their data from relational to a graph database just to do the analytics? So basically we have kind of a database that has a graph model, assume that's a graph database, and then basically, and even there, the choice of model is important, right? So phone address is a node, not a property. So in here, I modeled basically address and phone as nodes, not properties, so that I can actually essentially run fraud detection pattern on that, right? But I could have easily modeled address and phone as properties in the property graph model. So if I chose property graph model, if I chose RDF, I'm forced to do this. So I immediately can do the fraud detection pattern. If I chose to go property graph, I had that choice of picking these as property, in which case it would have been much harder for me to express that pattern. I've had to kind of do something extra. So here the question is, well, in my database also already my data is probably relational. So could we, typically you have database, it has this table, you do an ETL into this other database. You construct your graph model, and then you do your graph analysis, right? So the question is, well, what's the DSL for creating a graph from tables easily? It would be nice to have that. And how do we make this ETL step fast? Or can we actually skip this intermediate database, graph database, in between? Can we actually just construct a graph view from a relational data and run analytics engine? So that's kind of what we're proposing is maybe you have a database. When you want to do analytics, you actually just create a virtual graph model, kind of like a view, and then you do your analysis on that. So great tool. We think Graph is a great tool for data analysis, but do we need a whole new database engines for it? We propose adding the missing piece, which is the analytical engine, but use conventional databases for the transactional piece. And we have a bunch of issues and questions about graph data models. So that was my talk. So I want to also talk about Oracle Lab support for LDBC. So we've been spreading awareness of LDBC among relevant Oracle organizations as well as externally. We've initiated and funded the GraphBench work at University of Washington. Before being aware of LDBC and upon awareness, we've directed those folks to collaborate with LDBC. And Jacob is here. Poor guy being forced to use the social networking benchmark, but I'm sure that was a good experience. We also now funded Alexander Yusuf from TU Delft to join the LDBC effort, again to fill in that analytical gap in addition to UPC. And Alexander set for himself an aggressive target of February for initial draft document. I basically asked him, produce a document like they have for SNB, but for graph analytics. He's like, okay, we can do it by February. So we'll see. He's confident. So just finally want to close my own thoughts on LDBC. I really like the choke point based design. It's a great approach and should be pursued even for the analytics workload. And I already see some disparity, like the semantic publishing workload doesn't use it as well as the. I just think it's a good principle. Let's just actually use it for all the workloads. Social networking versus semantic publishing should be mostly about dataset characteristics and not about orthogonal issues like inferencing or choice of implementation, whether one is Sparkle or not. And actually, the actual dataset is an important dimension that affects the implementation design choices, both algorithmic, which algorithms we're going to use, but also runtime. So I believe we need to add more data sets and convince ourselves that the data set cover actually a good range of use cases. Again, a choke point-based approach to data set selection. And we need to, I really like the what div, we need to compare the characteristics of these data sets. Are those looking like semantic networks versus social networks versus web graphs? These are all different. Also recommend to expand the group makeup to include the board to include end user representatives that are actually using the systems as opposed to just vendors. That way we can actually get guidance in terms of the choice of queries and future data sets. And also highly recommend spawning a sister organization for standardizing APIs and query languages that are graph-oriented but don't fit within the W3C standard, which is very much web-centric. If you don't have a URI, they don't want to talk to you. So that's what I have. Thank you.
Thanks, Hassan. Are there remarks or questions on Hassan's point?
Well, it would seem that I would agree that extending relational core database functionality in certain directions, such as putting recursion in there or better, and possibly extending data types and so on, is possibly introducing also some schema lastness, like Vertica has done, has a great promise. And then maybe at the very core engine level, there does not need to be a strong divide between RDF, property graph, and SQL. There we would tend to agree. As for this making these graph extraction, memory-based graph extraction of some other kind of database, that again seems to make good sense. So you have a valid points, we find.
Thank you.
Anybody else?
Do you plan to have this in-memory analytics accessible to Sparkle, or that's not on the roadmap?
Yes. Accessible in the sense that you can load RDF data. It will automatically, very much like what Olaf, but not as principled, but yeah, we treat the literals as, properties and the URIs as edges. So it will load most RDF data represented as property graph, and then you can invoke analytics on it. So we have an RDF loader for that. Yeah, but I could imagine going beyond that and having a call, like a function you can call, get some data, and then use Sparkle to query that. What we notice is people don't want to just do query and analytics. They want to do maybe a little bit of querying, a little bit of analytics, a little bit of query, all in one kind of workload, right?
Okay, thanks.
Thank you.